So today we will like to continue our discussion on topology. Last day I have given you a brief idea about the topology, but as I said that it is not at least my objective to, and even I am not the right person to train you with the abstract concept of mathematics, and that is not required. We are engineer, we are not theoretical physicists or means abstract mathematicians who will be means enticed by the abstract structure of any set, or like who can imagine whether a spin sorry an electron is executing a spin or a nutrition, or means whatever they may have their own world, but we are the engineer, we are the kind of more materialistic, more coarse people who are very means we love to connect with the reality. Means reality means not reality means very blunt reality. So here, instead of considering the abstract definition, I would like to cite more and more examples, and that is why instead of claiming that letter, which letters are topologically identical, like, and so instead of means following all these classic books, here I have taken the snap of this classic book. If you want, you can follow it. In my opinion, it's a very good book and very means easy to read. Like it will be your means lean session. You can pass your time. It will be a great time pass. Only number of pages are say 140, right? Including the table of content and index. And if you read this kind of books written by the mathematician, where you will see that they are doing like they are trying to prove how E, or means rather not prove, rather showing that E, F, T, Y, how all these are homeomorphic in terms of topological description. I am showing you just to means give you or means kindle your interest in this area. So how E can be converted to F, like if you just do a little bit of manipulation, like if you take an E shape made up of rubber and then you just do this and then first rotate this base by an angle 90 degree here, and then just this is, as this is made up of flexible element, you just means try to compress it to a shorter height, then you will get F. Similarly, by doing in other way, you can means doing any kind of manipulation with the shape without cutting and gluing, you can realize any shape between these four, and they are like, while the people who are in geometry may find that there is an angle here and here and here, namely 120 degree, here it is 90 degree, but the topology people are quite happy, because topology, I told you in the very first lecture on topology that they are interested in the only the similarity of means they are not concerned that how the things are connected, rather who are present in the set and how they are interrelated, that is very important to them. Now instead of going to this abstract field, what is my idea, I would like to start our discussion on particularly in, even in the last day, if you follow my last lecture, it was quite means example oriented rather than proof and proposition oriented. And today also, I would like to start with like Euclidean topology, and means gradually I would like to go to the discussion on basis and other things. Why Euclidean? Because we, the engineer fellow, find it very comfortable, at least myself with my limited ability and intelligence, I find myself very comfortable whenever I am in Euclidean field. I can feel it. Even by looking at an empty room, I can feel it's a three-dimensional vector space. It is having three, means the three walls are that kind of uh, two-dimensional subspaces of. So I can feel it. So whenever we are in Euclidean space, it gives us advantages. And that is why instead of means trying to recognize which letter is homeomorphic to which one, or sorry, which alphabet is homeomorphic to which one, we will directly jump to the main content. That is, last day I defined topology and open set, closed set, and today we will start our discussion like if we have two topology tau and tau dash, then like both of these are defined on the set. Now one question can comes in our mind, so quickly revise that what need to be there if we want this topology, means tau is a topology. So what is needed to become a topological set? That are collection of subset of a set X, that is tau is said to be a topological space together with X if we can see that X and the null set belong to our tau, and then second one is that any arbitrary union of elements of tau is in tau, and third one is any finite intersection of tau is in tau. So these are the three things. However, now suppose you have two different collection of set tau and tau dash, and both of them are satisfying these three property. Now, as topology is related to these kind of things, now we one thing can come in our mind, that which one is slightly lighter, or means set which one is which topology, you can say that it's a kind of fine topology, and that one is a heavy topology or quartz topology. So then we can say that if tau dash and tau, if tau dash is contained in tau, just a minute. So here, if this is the case, tau dash is in tau, so we can say that this is our superset, this is our subset. Now if this tau dash properly contains tau, sorry, tau dash, this one indicates tau dash contains tau, then what we can say that the topology tau dash is finer than tau. And similarly, if we have something like your tau dash properly contains, like we can write this this. So what does this indicate? This indicates that it properly contains the other set, right? Now here, if tau dash is like tau dash properly contains tau, then what you can write that tau dash is strictly finer than that of tau. And conversely, what we can say that if tau is contained in tau dash, we can say the topology tau is coarser than tau dash. And obviously, for properly, yeah, you can write it. They are properly or means uh, strictly coarser than that. If tau properly contained in tau dash, then you can write that tau is strictly coarser. However, now you have to understand that what does it actually means physical word. What does it mean? Now you can consider like a truckload, like a truck or any means cart or anything that is full of your like your say truck is full of gravels, right? Now what you are having or what you are trying to do, like if you consider the total gravel, right? Total that total truckload that is formed or full of gravel. So the pebbles and their unions or collection of pebbles, they are you can consider them. They are the open set, right? Now, if you by means of some hammer or something, if you smash them in powder, right? So if you smash them in powder, then what would happen? If you smash them, then like collection of open set. See previously how many pebbles you have and now how many granules you have. If you compare, then obviously the number of granules generated by smashing of your gravels is means you can think about the cardinal means by means of cardinality of the two sets. If you consider the cardinal number of the same truckload with gravel, then you suppose you got something n or something, and now after smashing it in means dust, then obviously your cardinal number will increase to a very high value. And the second one, you can say always the second one is having like so basically what you are doing in reality, you are doing that tau means you are means uh, what to say, like if you make gravels finer, then one time after means repetitive operation, you will get a dust particle. So similarly, what means in our discussion, which cell contains that dust particle? That is the tau dash, right? So that is you can see here that if tau contains tau dash, Then tau dash is strictly finer. And if one is finer than other or coarser than other, then these two sets are said to be comparable. Like when you will say comparable, like both of them should contain each other. For example, let me give you one more example that will help you. Let us start with a set. A set, say, right, or let me repeat, means represent them pictorially. What is the cardinal number? 3. Now, what are the topologies you can generate? This is obviously a topology. The set on itself, it's a topology. Now you can generate this also as a topology. Like if you here, what is the topology? Here, what is the topology? I know I have discussed these examples, means in I mean some expression in my last video, but now from diagram how to write the expression, that is we should know, like x pi, and here what are the elements you are having, c, then a and a comma b. So this is the topology. Now you can see that another topology, what could be the another topology? This is very important. This concept of topology is very important for us, for the control system engineer, like what a topology is. Now, if you consider don't you think that this one is finer than this? Isn't so? And if you consider one more topology on that same set, I'm using different color just to make you understand that what are the things we can have here. So if you consider, so what about this? Like this one is finer than this one, and this one, what about this one? Uh, it is your task to determine between these two which one is finer, right? So obviously I hope you get certain idea about that finer and like coarser. A few mathematicians call it like this concept that you will be more delighted because their notion is somewhat relatable. They claim tau dash is larger, sorry, they tag tau dash is larger and tau is smaller. So which we consider it's finer, they claim it's larger and this one is coarser. Right. So now let us move to a new topic that is very important in the context of topology, that is basis of a topology. So what is a basis? Means now after certain time you may feel or start develop feeling that why are we reading this topology? Because now we will gradually will develop a notion that vector space and topology, what is the need of topology? If we have a vector space like, and whenever we are in two-dimensional plane, obviously if we want to consider higher dimensional plane, we can consider just by we have to consider more number of basis vectors to span that space. So why it is so special in there in topology? What means we could not discuss or means cover up with our normal vector space? Why do we need topology? Anyway, we'll gradually get that answer. Now here it is that one thing means in a very nicely and blatantly you can figure out that in case of your vector space you need additive inverse, these, that. Here all those restrictions are quite means are not present. Here it is just like the union. So you can consider that union is something like what we are claiming that addition, but not union should not be compared with addition. So because union you are getting a larger set and in addition you are actually trying to act two vector together anyway. So in that vector space you need to ensure closure with respect to addition, closure with respect to scalar multiplication, or closure with respect to that means uh, multiplication. However here it is very simple. Your things are quite simple. Just you have to check whether the main set on which you have formed the topology, that is there in the collection of subset tau, and also the by default null set is a member of all other set, so you will get that. Then the second thing is that your union, any arbitrary union of those open sets should result in a member of your topology, and any finite number of intersection in a topology should result in a topology, means a member in topology, right? Now let us define the basis of a topology. So what is basis of a topology? Like if X is a set, basis topology on X is a collection beta of the subsets of X called the basis element such that for every x, small x, element belong to the set capital X, there exists at least one basis element B such that B contains small x. So what is the issue here? That for each small x belongs to your original set capital X. Small element means small x denote element in capital X. There is at least one basis element B containing small x. Now another one is required, that is if the small x belongs to the intersection of two basis elements, say let us consider basis elements are B1 and B2, then there exists another basis element B3 that is there such that x belongs to B3 and B3 is a proper subset of, or means a subset of B1 intersection B2. So let me again try to give you a pictorial representation like on a set X. So what we can do, like as I told you that we'll take examples from Euclidean space. So let us consider that this beta or this is the collection of all circular regions in the plane. So in the two-dimensional plane you can have infinite many such circular regions. So how can you mathematically define a circular region? Like mathematically you can define a circular region is when you know the radius, say this is your space, it is your origin, and you want to define a circular space, or not even origin, say here you are considering a circular space with respect to this point C, then obviously how to define that set, your all the points where say any other point is having coordinate a comma b and this one is having c1 comma c2, right? So how to define it? It is like root under a minus c1 square plus b minus c2 square should be less than is equal to r. So r is what? R is the this radius of this circular region. Now if you consider you are trying to fill up a two-dimensional plane, you can take a different circle of different radius and let them overlap, and gradually they will span your hierarchy. Yes, and for your ease of visualization, you can do it like here it is a circle, this is a circle. Now you take a different circle. Gradually, if you keep on means allowing them to overlap and means fill up the space, gradually they will fill up the plane, right? So what is the issue here? It's very simple. Like what I'm trying to say is that any circular region in two-dimensional plane is a topology. Now let us check whether they can form a basis or not. Let us draw two circles. Even without knowing the origin of the coordinate system, we can always draw two circles, right? My drawing is bad, that is a problem, but try to understand that this is a circle, right? A regular circle, not this kind of means. So what is here? You are considering an element x. So what is our proposition? That first one, that for each x is a set, x is a set. So let us consider that set x is which set? The set that contains all the points in our two-dimensional plane, right? So a basis topology of capital X is a collection of beta of the subsets of X. So what could be a means feasible subset? A circular disk of different radius. They can be a physical subset, physically realizable subset. Now small x is what? Small x is a point on that two-dimensional plane. So even for each and every small x, you can always define on this. This is the beauty of Euclidean space. You can always define a circle around that point, whether its radius is 1 light year or the radius is in like picomillimeter range. It doesn't matter. What does matter is that you can always define a circular disk around them, and you can see that for any other two arbitrary circle, you will always find whose intersection, whose any other two arbitrary circular disk, you can always find whose intersection is forming a subset here, and this B3, the new one, the disk around your point of interest, is a member of or contained in that set. So that is very simple thing. Now what is need to check that, or what we can say that if B satisfies these two conditions, then we can say the topology tau is generated by our this beta, right? So what is the condition? That how we can say beta is a basis, that the Now, like we have already studied the notion of it. We have already studied the notion of open set, like any subset U of X, capital U of X is said to be open if it is a member of our means topology tau. So, if for each X that belongs to tau, you can always find that there exists a basis element capital B belongs to small beta. So what I am trying to say, that for all X belongs to U, such as U belongs to tau, right, U belongs to tau, there exists a basis element B belongs to the collection set beta such that, already I have written such that here, but still such that like so for two condition now, so we can write for all X belongs to U where U is the open set and such that U also belongs to tau, there exists a B belongs to beta such that X belongs to this capital B. B is an element of our basis, and also we can show that B belongs to U. So what is it we are trying to say here, that if means if we say that beta satisfy the two condition of basis, then we can also further prove that any subset capital U of capital X is like, and we can pick up an element capital B from the basis set beta. Beta is the set of all bases, B is a single basis. Now we can pick up capital B such that the element X belongs to B and B also contained in capital U. So we can prove it, but it's not that important. But what is important to note is that, like for all X we can find this kind of X belongs to U, a subset of capital X, we can find out a B. Like beta is a basis vector, so beta is having infinite number of this kind of circular disk, right? Now you will be surprised to know that, like in case of a vector space, what we have say, for if we want to span a three-dimensional space, we need three vectors. Like if you use rectilinear coordinate system, then it's x, y, z. Now if you go to curvilinear and spherical polar coordinate system, then it will be that r theta phi. And if you go to cylindrical, so basically if you see that these r theta phi, they are orthogonal to each other, and also the rectilinear xyz, they are orthogonal to each other. So we can say that both of them are bases, and in three-dimensional plane both of them are working well as a basis. Similarly, when we consider the topology, when we are about the topology of whole plane, whole this two-dimensional plane, right? So a two-dimensional plane is a topology. Now you take it, and then the basis could be uh, circular disk of any number, or you can have another basis like you can conceive of having basis as rectangles whose sides are parallel to your axis. So this is B, this is this is B1, this is B2, and here you have another B3 whose center is at X. So you can always find this kind of different basis for a given topology. Now let us understand one thing, that I am intentionally drop the, or means not dropping, rather I am not focusing more on the discrete topology, because in our case, at least what my purpose is to develop a notion of continuous topology among you. It is not that we are having some discrete elements present in us and we are trying to figure out the topology. Rather, here we will be dealing with spaces, means or means systems that is nonlinear in nature, and therefore we need to know a continuous kind of topology. You will have infinite number of many points, and you can have different basis elements. Anyway, now see what we can write. Let us write a few important lemma. That the first lemma, I will sometimes drop the proof, because if we can understand the proof intuitively, then there is no point of dwelling with that proof. We are not mathematician, we are just means engineers who want to use these tools for representation. Then tau equals to the collection of all union of elements of beta. So this is also a very easy thing to understand, that if we have a set and beta be a basis topology for a given topology tau on X, then tau equals to the collection of all union of elements of beta. So as we are somewhat conversant with vector space, let us try to understand it in that notion of vector space. Obviously, again and again I am telling you that vector space and topological space are totally different, but still you can figure out a bit, means, or find, or means find yourself a bit more comfortable situation. Like if you have a three-dimensional space over your field of real number, then obviously what will be your basis? Your basis will be three basis vectors will be there to span your space, and what you will see that these like any point, right, any point you can write it like, how you can write it, like 4 comma 5 comma 6. So you can write it like 4 1 comma 0 0 plus 5 0 comma 1 0 plus 6 0 0 1. So in that way you can think about when you are having this tau, where tau is the collection of all, means tau is like, means at the space. Tau is means like that R3, and you are having this basis beta. So in that case you are having basis vectors 1 0 0 0 1 0 0 0 1, and here you are having basis elements of beta. So obviously if you take that all the union of beta, then obviously that will give you the entire space. Or you can means prove it when you can very easily show you to you, like you can have a collection of elements of beta. Then what we can consider, this collection, whatever be its name, is also belongs to your original topology tau. They are also the element of tau. So collection of elements means what? You are picking up a few elements, like you are picking up B1 union B3 union B7 B8. It's like that. Suppose you are having Bn number of elements there. So what we can claim, that as all these are the elements of topology tau, so their union should also belong to tau, right? So sorry, their union should also belong to tau. Now what I am trying to claim here, that this like conversely given, if we consider that we are having, say, element u belongs to tau. Now let us select one x, one element x that belongs to this capital U. So, and we can figure out an element Bx for all such x such that x belongs to Bx, that contained in this U. So if you consider U, this U can be written as this big cup this is big cup, this is U, do not get confused. So we can use another color. So here this Bx, so it equals to what? Equals to all the unions of such bases. So quickly once again let us just see what is the theorem lemma. This one is very important for us. Let x be a set and let beta be a basis of topology tau on x. Then tau equals to the collection of all union of elements of B, right? So now from here one further means interpretation we can draw is that, like this lemma states that every open set in our capital U in X, that too can be expressed as a union of basis element. Or stated other way, it is trying to claim that every element in your topological space can be expressed as an union of your basis element. Here, let us write a very few important findings that every open set that is member of tau in uh, this topological space x comma tau can be expressed as a union of basis elements. Now, one thing you must not forget that although I am trying to relate the linear algebra's concept means or although giving some analogy between linear algebra and this topological space, although they are quite different in each other by virtue of their composition. But one thing it is why the basis definition is drastically different from linear algebra is that in case of your linear algebra, in linear algebra, an equation expressing a vector is an unique combination, right? As a linear combination in your space. However, in case of topological space, that we can have different ways from the basis to a topology, and that one is not unique. Like what we can write that the here I have written already that we can write every open set can be expressed as an union of basis element, but this expression this expression is non-unique. Please keep it in your mind. So how this topology and the vector space are different, and intuitively I would like to ask you that intuitively try to find out that why in case of linear algebra it is so unique, so rigid, but in case of basis we are saying that it is not unique. Why so? Whenever you will get stuck and try to figure out the answer by yourself, then only you will be able to learn. Otherwise there will be no such, means proper learning will not take place until unless you get stuck to a difficult situation, you find yourself in a difficult situation and try to means figure out the solution by your oneself. Now, another important theorem I would like to write here, that if B and beta and beta dash are the basis for the topologies tau and tau dash, respectively on x, means both of them are on x. I am not writing it, it's just irrelevant. So then the following statements are equivalent. Following statements are equivalent. What are the statements equivalent? That one statement, tau dash is finer than tau. Another statement, for all x belongs to capital X and for all B belongs to beta, that contains small x, there exist a basis element of beta dash set B dash such that x belongs to B dash x belongs to B dash that contained in B. So here I would like to like go for the proof, because the last line is is slightly surprising, because you can see here that x belongs to beta dash implies beta dash contain in B rather than B contains in means beta dash contains B. It is not the case. Like B is seemingly B is larger than beta dash. So why it is so? Let us investigate that. We are claiming that, let us start from 2 and then try to show that 2 is equivalent to 1. So given an element capital U of our topology tau, what we wish to show that U belongs to tau dash also. Now let us consider that x belongs to U. However, you must notice that since beta generates tau, so by virtue of the definition of basis, there exists an element capital B, capital B. Such B belongs to this beta such that X belongs to B that is contained in U. Like B is not contained in U or not, I am not going to tell that. X is contained in U. So if that is the case, then similarly, we can say that beta dash belongs to beta, sorry, B dash belongs to beta dash such that X belongs to beta dash is contained in X belongs to beta dash contained in here we have written that this one, so contained in B. So X belongs to our B dash contained in B, right? Now if that is the case, then what we can do, like we can see that B is contained in U, so we can write that X belongs to B dash contained in U, right? So if X belongs to B dash contained in U, so U belongs to tau, that we know, it is by definition, it is the case. So if that is the case, then we just need to reach to the similar thing by starting from 1 to 2. So in 1, what we can say that X belongs to capital X and capital B belongs to beta such that X belongs to B. Now that capital B belongs to tau, and by definition here we have written tau is like tau dash is finer than tau, so tau is a subset of tau dash. So if that is the case, then B, as it belongs to tau, it is obliged to belongs to tau dash. Sorry. Now that is tau dash is generated by capital B dash, then there is an element B dash belongs to beta dash. Sometimes I get means right means while pronouncing I make mistakes like tau is generated by beta dash, I write it b dash or but don't get confused that do remember the set beta or beta dash are the basis and capital B are the elements. So the beta, the set has the power to generate. Like in although in topology the basis and linear space basis is completely different topics, but you can see that in linear space also one base vector or basis vector cannot do anything, but the total set when you take the three vectors together they can means point any element or means map in, sorry, not map, rather they can express any element as a linear combination. So similarly when you are talking about, like in case of linear system, those three vectors together can generate or span that space. Similarly here, your beta or beta dash, they can only span the space, not a single element of your basis set. So it is not beta, sorry, if I think I made a mistake by saying it is b dash, it is beta dash. So whenever you are topology, I am talking about mapping or generating a topology, it is should be the beta dash. So in that way, we can write that b dash belongs to beta dash. So that implies x belongs to b dash that contained in B. So once again, for your better understanding, we are having beta and beta dash. They are the basis for the topologies tau and tau dash over a set X. Then the following statements are equivalent, that tau dash is finer than tau, and for all x belongs to capital X, for all capital B belongs to beta that contains X, then there exist basis elements of beta dash of beta dash such that this B dash is contained in beta dash such that x dash, sorry, x belongs to capital B dash that is contained in B. Like B dash is expected to be a subset of capital B, while tau is a subset of tau dash, B is a subset of, sorry, B is the superset of B dash, right? The reverse one, right? So let us see how we can prove this equivalence, that given an element U of capital tau, we can see that this U belongs to tau dash. Now, why U belongs to tau dash? Because tau dash is the superset of tau. So if any element belongs to tau, it will automatically belongs to tau dash. So let us consider a small x, an element that is belongs to U, right? So this U, since this beta generates the topological space tau, there exists an element capital B belongs to beta such that this small x belongs to B that is contained in U, right? So what we can write that this u belongs to tau, it is by definition, then from 1 to 2 what we can get, that x belongs to x and capital B belongs to beta, then like then with capital B belongs to tau, capital B has to belongs to tau, and tau is a subset of tau dash. So we can write that beta is a subset of tau dash. So we can write tau dash is generated by beta dash. So there is an element b dash belongs to beta dash. So what we can write from here, like here we can write that there is an element b dash of beta dash. So x belongs to b dash, that is a proper subset of b. So here also we are showing that it is x belongs to b dash, which is a proper subset of b. Here also we are showing this. So means it is difficult for us to start at 1 and reach 2. So we are doing a halfway, like from 1 we proceed halfway, from 2 we proceed halfway, and prove that if we proceed, then both of them are giving us the same result. So in next class we will discuss standard topology and another few points, and then we will be ready to means discuss our control system things, because later on you can see that your all the functions can be expressed like product topology and others. So instead of discussing them now on, I would like to discuss them in my next class. Another 3-4 class on topology will be sufficient for us to understand. However, in my next class, like I plan to give you some basic intuitive idea in our next videos. Like those will not come in your semester question, but it may so happen that you do not have that knowledge. So you may find them as a companion video.